Quadrilaterals, Section 6, Video 2. In this video we're talking all about coordinate proofs, which are a little different than two-column proofs in that we don't have to necessarily write out all the reasons in a numbered order like we do for two-column proofs, but in coordinate proofs it's equally imperative that we show all of our work. So for these coordinate proofs that we're doing in this section, there's three formulas that we'll use a ton, and so I just want to do a quick review. They're on your blue packet, and you should all be familiar with them, but they're the slope formula, distance formula, and midpoint formula. So I'm going to quickly write the slope formula. We know is rise over run, so it's y2 minus y1 over x2 minus x1, and we call that m. We'd also call it the change in y over the change in x. It's just a different way to write it. You could also write it as rise over run. Those are just three ways to write the slope formula. And we remember that, quick side note, that if we have a horizontal line, m equals 0, there's no rise, so it's 0 over whatever the run is. We know a vertical line, m is undefined. We also know that those two lines are always going to be perpendicular. If one's m equals 0 and one is m equal undefined, we know that if two lines are parallel, then m of one equals m of the other. If this is 1 and this is 2, and that'll show that those two lines are parallel. And if two lines are perpendicular, we know that if the slope of one is called m, the other would be the opposite reciprocal, so it would be negative 1 over m, whatever the number m is. The distance formula, we should all be very familiar with that. It uses Pythagorean theorem to eventually, let's see, I'll go back to black. We subtract the x's and we subtract the y's. We find the difference or the change, and we square both of them and add them. And then if we do the square root of that, that will give us our length. So this is for length, and we use it to show congruent sides. That's where we use it in our coordinate proofs. And then we have the midpoint formula, which we'll use for bisecting sides. So whenever we need to show that something is bisecting another line, we'll use the midpoint formula. In the midpoint formula, it's an ordered pair. It's essentially kind of like finding the average. Like you add the x's and divide by 2, and then you add the y's, and you divide by 2. Great, let's move on to some examples. So this one is, what is the length of the mid segment? Well, for this one, there's a few ways you can do it. The way I like to do it is find the length of both of the bases. So I'll use the distance formula, and then I'll do the 1/2 times the sum of those two to find the length of that mid segment, that red segment. I'll show you a little shortcut after this one, but in general, this is the way you kind of want to do it. So I use the distance formula, and I'm going to find first the distance between these top 2 points. So I'm going to find, let's see, I'll grab a different color. This green, I'm going to find the distance of that. So first I subtract the x's, so I'm going to do 17 minus 8 squared, and then I'll do 6 minus 6 squared, which is going to equal 17 minus 8 is 9 squared, and that's 0 squared. So that's going to equal the square root of 81, which I know to be 9. So that's that green one. And then if I was to do the other one, I could write out all of the distance formula, but for this one, since it's on the x-axis, I can kind of just see that it goes over to 20, 0, so the length of that is 20. And so to find the red line, I kind of do the average of those two. So we know by the properties of the mid-segment that 1/2 times the sum of those, so 20 plus 9, which equals 1/2 times 29, which equals 14.5. You could also find the coordinates of the midpoints here on the side. So I could have found the midpoint over here, and I could have found the midpoint over here, and then found the length, use the distance formula to find the length of that red line that way. And just looking at that top base, I could have seen that they're both on the 6 y line, and so I could have just done 17 minus 8 and seen that the length of that is 9. Those are just some shortcuts, but in any example you can use the distance formula to find the length of both the bases, do 1/2 times their sum, and you'll get the length of the midpoint. Another example, identify the quadrilateral as specifically as possible. That means we only need to give one name, so we want to be as most specific as possible. I mean, to clearly show and explain our work. Well, for these, when we're defining things specifically, if you remember, if you look at your hierarchy, they're all kind of defined by having 2 pairs of sides parallel, 1 pair of sides parallel, or no sides parallel. So we either you start with a parallelogram, a kite, or a trapezoid. So I would start by first defining that. So I'm going to start by proving the sides parallel or not parallel. So I'm going to use the slope formula. So I'm going to say the slope, I'm going to start with AB. I know slope is rise over run, so I do change in y over change in x. So if I'm doing AB, I'm going to do change in y, 9 minus 3, over the change in x, do the same order, it's really important, y minus -1 equals 6 over 2 equals 3. All right, and then I'm going to do the opposite side to see if those two sides are parallel. I'm going to do CD. Change in y, 3 minus -3 minus negative makes that a plus. And then change in x, 3 minus 1. Make sure I did the right order there. I started with C and then I did D. 6 over 2, once again 3. So, therefore, AB parallel to CD. Great. But I need to show that the other two sides are parallel as well, so I need to do BC and AD. Because for it to be a parallelogram, I would need both sides of those to be parallel, both pairs. Right now, I only know that it might be a trapezoid, but I'm gonna see, because it looks like it might be a parallelogram to me. So I'm gonna do the slope of BC. So I'm gonna start with the y's, 9 minus 3, and the x's, 1 minus 3. So we have 6 over -2. Which is going to be -3, and then do the slope of AD. Start with the y's, 3 minus -3 makes that a plus, -1 minus 1, or it's almost like a plus negative. That's 6 over -2, which is also -3. So therefore, BC is parallel to AD. So I know it's a parallelogram. Now I need to see, is it a more specific kind of parallelogram? I do that, and I need to think about how can I prove something to be a more specific kind of parallelogram. If I know something about the diagonals, I could prove that it's a parallelogram. Now, I might not actually have to show any work for this if I do this in a clever way. So when I look at this, I see that this diagonal, it's horizontal. The slope is 0. And then if I go do this diagonal, I see the slope is undefined. So I see that these diagonals are perpendicular. And I know that for a rectangle, those diagonals will not be perpendicular, so it must be a rhombus. And I know it's not a square because those sides are not right angles. So, therefore, I can conclude, if I kind of cleverly put it, I don't have to show exactly that those diagonals are perpendicular. I can just explain. Therefore, ABCD is a rhombus because AC is horizontal and BD is vertical. So AC is perpendicular to BD, which by the proof of a rhombus we know makes that a rhombus.